Hi, we're going to have more examples in frequency response. These frequency response examples, it's using ideal amplifier, and sometimes we're going to use inductive circuit, capacitive circuit, just to get deep understanding of the frequency response before we start to do application to transistors. For this example we have an operation amplifier. So obviously it will be operating as a DC amplifier, and it's given the mid-band voltage gain, which we can write it AV mid-band. Usually this is the maximum value, so we can write equal AM, and the value is given 100,000. That's the value given here. You can write it like 10 power 5 high gain. And then the cutoff frequency is equal to 10 hertz. So you can say that the cutoff frequency equal 10 hertz. The roll-off rate of 20 decibel per decade. When you hear the word roll-off rate, it means that it's going to be decreasing, and the slope will be equal to negative 20 decibel per decade. That's the meaning of roll-off. Draw the ideal baud plot. Before I do that, I just like to sketch the frequency response, the exact one. So we have the vertical axis, which represent the voltage gain AV, and we have the frequency axis, which F. So we expect that at low frequency, the gain will be equal to 10 to the power 5, the maximum gain, and it start to decrease till it reach 0. The frequency or the cutoff frequency, which is equal to 10 hertz, if you go and you make a vertical line to intersect the frequency response at Fc, which is equal in this case 10 hertz, you will find that the value of the gain will be equal to the maximum value, which is equal 10 power 5 divided by square root of 2, or in other words, you can multiply 0.707 by 10 to the power 5 would be the gain. That's the frequency response. What about the baud or the decibel voltage gain? I will show you the exact before I do the ideal. The exact will look like that. You will have the vertical axis, and that's the in decibel, the AV in decibel, and you have the horizontal axis, which will be the frequency, and we are using logarithmic scale, the semi-log paper, if you remember in previous lecture, but just I'm using here normal paper, So what is the value of the maximum gain in decibel? We know that to find the value in decibel, let's call it M, that's equal to 20 times log to the base 10 to the value itself. I want to find the value for 10 power 5. That's the 10 power 5, the gain in this case. So it will be equal 10, and log 10 power 5 just simply is equal 5, so it's equal 100 decibel. So I know if I make a line here, that will be equal to 100 decibel. And then start to decrease. All right. What is the value at the cutoff frequency, which is equal to 10 hertz? All right. We know that at the cutoff frequency, the value will be dropped by 3 decibel at the cutoff frequency. What does it mean? It means that the value of the gain at cutoff frequency will be equal to 100 minus 3 decibel, which will be equal to 97 decibel. So always remember that at the cutoff frequency, the value of the gain will be decreased by 3 decibel. So what is that? That's the baud plot for the magnitude, and this is the exact one. What about the ideal? The ideal baud plot, it's very simple. All what you're supposed to do, you will have the frequency axis F using logarithmic scale, and you have the vertical axis, which is the voltage gain in decibel. Now we know that the value that 100 decibel before the for the cutoff frequency, you make like a straight line, and at what value? 100 decibel. What's 100 decibel? We just calculated. That's in front of us. 20 log the gain itself, because you know that AV in decibel, it's always equal to 20 log base 10 to AV, and AV in this case is equal to 10 power 5. We got 100 decibel, but you stop at the cutoff frequency, which is equal to 10 hertz, and the roll off is equal to 20. If you remember this word, just to mention, it said that the roll off rate of 20 decibel, we said that means that the slope will be equal to negative 20 decibel per decade. It means it's going to be decreased at rate equal to 20 decibel per decade. So the slope of this straight line should be equal negative 20 decibel per decade. You see, remember that this is the approximate. We say at FC, at the cutoff frequency, we know from the exact one it has to decrease by 3 decibel, but just in the ideal one, just make a straight line so it will not be shown the 3 decibel. And then it will decrease till it reach 0 decibel at this frequency. So if it's required to find this frequency where the gain will reach 0 decibel, and it has a name, they call it unity gain frequency. So what's unity gain frequency? Unity gain frequency is the frequency at which the gain in decibel is equal 0 decibel. 0 decibel. Okay. And why they call it unity gain if it's equal 0 decibel? Because we know that log 1 is equal 0 decibel. That's why we call it the unity gain. So understand, when you have 0 decibel, it means that the gain is equal 1. Okay. So how can find FU, or the unity gain frequency? Okay. I have a nice formula that you can use it to calculate it. I will say FU is equal FC, the cutoff frequency, multiplied by 10 to the power of A decibel by 20. Don't forget this one. That will get you the unit. So FU is equal FC. FC in this case is equal to 10 hertz. So it's equal to 10 hertz times 10 to the power of the gain in decibel, which is equal 100 decibel, divided by, that's the gain, that's AV decibel, divided by 20. Why 20? Because the slope is equal negative 20, or the roll rate is 20. So that will be equal to 10 hertz times 10 to the power of 5. Yeah. Right? 10 to the power of 5. What that be equal to? 10 to the power of 6 hertz, which is equal to 1 megahertz. So in this example, we can find that at frequency equal to 1 megahertz, the gain would be equal to 0 decibel. So that was a simple example, but just to show how we can solve this kind of problem. Okay. And remember, this always, when you look at it, you know, it's DC gain. What does it mean, DC gain? DC amplifier? It means that below frequency you find that the gain is high, and then every time the frequency is increasing, the gain is decreasing till it reaches the unity gain 1. Okay. Actually, there are some circuits that it can be used to get the same characteristic. So I'm going to show you lag circuit. What's lag circuit? Lag circuit consists of resistor and capacitor, and that's the signal input, and that's the output across the capacitor C. We call this lag circuits. Okay. we need to find the frequency response of RC circuit in this way. So we know as first I will use voltage divider, but before I do that, I got to find the impedance of C. The impedance of C, as you know, ZC, it's equal what? It's equal J XC. And we know that XC is equal 1 over omega C, and omega is equal 1 over 2 pi F. So in this case, we are going to replace C by X of C by the reactance. And now I can apply voltage divider rule. The output voltage across the capacitor is equal to the reactance of the capacitor, which is equal XC, divided by the total impedance of the circuit, which is equal to R square plus X square root. That's how you find the total impedance, the magnitude of the impedance, because we know impedance is a complex number. It has a magnitude and an angle. I'm just interested here in the magnitude. So multiply it, of course, by voltage input. That's the current divider rule. So the gain will be equal the output voltage divided by the input voltage, and that I will call it the voltage gain. And I'm interested only in the magnitude. And I'm going to drop just this, and I know that AV is the magnitude only. That's equal to XC divided by R squared plus XC squared. I'm going to divide the top and the bottom by XC. So I multiply here by 1 over XC to get rid of it. And I multiply here by 1 over XC. So that will be cancelled. So I have the gain is equal to 1 over, and I have 1 over XC. If you want to enter XC inside the square root, so we have to square it. Why? Because 1 over XC, sorry. Because you know that 1 over XC is equal 1 over XC square root, right? So when I do that, I'm going to multiply each term inside the square root by the value of 1 over XC squared. So you have R squared over XC squared plus XC squared divided by XC squared, square root. That would be equal to 1 over R plus XC all square plus 1 square root. What is the value of R over XC? To find this value, just let's take it step by step. What's XC? XC, we found it here. It's equal 1 over 2 pi over FC. 1 over 2 pi FC. So what is the value of 1 over XC? 1 over XC will be equal to pi FC. So what is the value if you multiply this by R? So you will have 2 pi FCR. So R over XC is equal to pi CRF. I will keep this together in one group, and I will call this term 1 over FC. So now I can write this term as F divided by FC. So R over XC, I will write as F over FC, where FC is equal 1 over 2 pi RC, as I explained here. So now the equation is really simplified. The equation for the voltage gain. I have the voltage gain 1 over R over XC squared, which is now is equal F over F of C. So I will write it 1 over square root F over FC squared plus 1. So I simplified this RC circuit by this simple expression. Now I will just do two simplification. I will say what happened if F over FC is really smaller than 1. It means that F over FC squared will be much less than 1. It's like 0.01 1. So you can neglect it. If f over fc square less than 1, so you can ignore it and you can simplify what inside the bracket. You can now write a v equal to 1 over f over fc square plus 1, and this one is very small, it can be neglected. It will be like 0.001 plus 1, just 1. So in this case, AV is equal 1. So what I got here, I got this very important relationship. I can say the voltage gain almost equal 1 if the frequency over fc less than 1, or you can say when the frequency less than f of c. So if the frequency less than the cutoff frequency, the gain is equal 1. In this case, you can say that the magnitude in decibel, all right, or you can write AV decibel in this case equal to 20 log 1. What's log 1? 0. And 0 times 20 is 0. So this 0 decibel. So when I get 0 decibel, when the frequency is less than FC. Just write that when F less than FC. For this circuit will be 0 decibel. All right. Let's take the other situation. What happened if F greater than C, FC? If the frequency F greater than FC, it means F over FC greater than 1. Like 1.5, 2, 3, something like that. What about if you square the value? Will be much bigger than 1. If you have, for example, f over c equal 3, we square it be 9. 9 is greater than 1. Right. So if you do that, what does it mean? It means that the square root f of fc square plus 1, and this one is much bigger than 1, so 1 can be neglected. So you can say it's almost equal to f over c fc square root, and then the square root will cancel the square inside, so it has f over fc. So in this case, you can say that the voltage gain in decibel equal, I will go back to the expression, 20 log 10, and I supposed to have the expression 1 over f over fc square plus 1. And I approximate, or I round this expression to 20 log 10, 1 over, and the square root, I already proved it, in this case would be equal f divided by fc. So what's equal to? Let me just write it here in space. We reach this 20 log 1 over f over fc. When you are dividing in logarithmic subtract, you say 20 log, of course, base 10. The top, which is equal 1, minus 20 log the bottom, f of over c. What's log 1? 0. So in this case, the voltage gain in decibel will be equal, that's equal 0 minus 20 log f over fc. When this happens, that's when the frequency is greater than fc. So simply, I can summarize what we did. If the voltage gain given as this, and I just prove it, f over fc square plus 1, we say that we have two situations. One situation when the frequency less than fc or equal. What we'll get that the decibel will be equal to 0 decibel. And if we have the frequency greater than or equal f of c, so we have the voltage gain in decibel is equal negative 20 log f over fc. So how we sketch this? Very easy. We have 0 decibel when f less than fc. So let's say that this is fc. All right. So we'll have 0 decibel before that. Any frequency less than fc will have 0 decibel. What about if f greater than fc? You have negative 20 log f of over fc. It means the slope of this one is equal negative 20. But I wanna just tell you how even you can get some value so you can sketch it exactly. I will show you a very nice one. It's a substitute. How is substitute in this equation? All right. You will say that what about it's equal negative 20 log f over fc. What about if f is 10 times fc? If f equal 10 times fc, so f over fc will be equal 10. What's log 10? 1. So the whole value here of this one will be equal 1. 1 times negative 20 will be negative 20. So when f equal 10 times fc, you will have negative 20 decibel. So all what you're supposed to do, you go in the logarithmic paper, and if you say if you are increasing this by 10 times, you reach 10 fc, you have to go down by 20. Or you get negative 20, right? And then you connect these 2 points. And you can extend it. Again, how we did it? Said that what happened when f is equal 10 times fc. It means 10 divided by fc is equal 10. So you go to the equation f over fc is equal 10. Log 10 is equal 1. 1 times negative 20, negative 20. So when you have the frequency here equal 10 fc, then the value of the decibel equal 20. Tell me how you know 20. Already you have this is 0. And this is, you mark this negative 20, negative 40 decibel, negative 50. And anything above will be 20 positive decibel. That's all in decibel. You go for negative 20, add 10 fc. You put the point, you connect. So that will have a slope equal to negative 20 decibel per decade. So that will be the response. Of course, that will be your frequency axis. That's f. All right. So that's the way that you would. But by the way, you got the same thing. You see, you got straight line and then decreasing by slope 20. That's for what circuit? For the lag circuit. So lag circuit, when you have capacitor on the output and resistor connected to the source. It's similar to the DC amplifier. It was, but it was not 0. It was not 0 decibel here. It was a value, constant value, and then decreasing by slope is equal negative 20. That's the way that DC amplifier behave, and that's the way that the lag circuit behave. What's lag circuit? When you have RC circuit, the output across the capacitor and the input connected to the resistor. All right, great. And that's example. That's example for lag circuit. In this circuit, draw the ideal ball plot for the lag circuit. Of course, I'm not going to do the same thing I did it, but I will find from here the cutoff frequency. What is the value of the cutoff frequency? The cutoff frequency, as we proved, Fc will be equal 1 over 2 pi RC. In this case, 1 over 2 pi, and the resistance is equal to 5 kilo ohm, and the capacitor is equal 100 picofarad. Substitute by the quantity that you have here. Let me just calculate. see how we can get value here. It's equal 318 kilohertz. So that's the FC. So when you sketch this circuit, it will be just what we got. Let me just move this one. We learned that, let me show you the RC that we get. 0 decibel, and then at FC go to slope -20. So I'll just do the same thing. That's the frequency axis. But I have here the cutoff frequency 318 kilohertz. And if I multiply it by 10, so you'll have 318 kilohertz. That will be equal to 0 decibel. And at this value, it will go down to -20 decibel. So you go there, the 10, the second point, and connect. That will be the baud plot of this one. Okay. That's simple. Let's say that if they ask what is the value, let's just say what is the value of the voltage gain in decibel at, let's say, frequency 31800 kilohertz. At any frequency, you want to find the amplitude of the voltage gain in decibel. So I'll say EV in decibel at this frequency. I know that the frequency 31800 kilohertz, it's already bigger than FC. This frequency is bigger than FC, so I'm going to use the formula that we just proved that it's equal 20 log what. Let me just look back again. What is the -20 log F over FC? So it's equal to -20 log F over FC. In this case will be equal -20 log, and the frequency is equal 31800 kilohertz divided by 318. That's FC. Let's simplify it. This cancel will be 100, so you have -20 log 10 100. So log 100 is equal to, so you have -20 times 2, that's equal -40 decibel, which is expected. So it means if you go to this frequency that's given, 31800 kilohertz, if you go there, then you will go to -40 decibel. Okay, that's enough for this one. Let's just go now to another thing. This circuit is different a little bit because the output is across the resistor, not across the capacitor. So this is not a lag circuit. That's, we call it lead circuit. So lead circuit, when the output across the resistor, and we are going to when we go back to the AC amplifier using BGT, you will find sometimes you will have the capacitor on the output, sometimes there is on the output. That's why I'm explaining both circuits. So in this circuit, it's given the same values that we did last time, but we flipped it. The output, it's across the resistor, all right, not the capacitor. So obviously we are going to have different transfer function. That's and also there is an amplifier here, that 100,000. So let's just first, how can we find the voltage across the resistor R? All right, I will say that the voltage across the resistor R, VR, I'm going to use the voltage divider. It will be equal the input voltage times R divided by the total impedance in the circuit, which is equal R squared plus XC squared. Okay. And this voltage across the resistor, VR, is going to be here, which is input to the ideal amplifier, which has gain 100,000. So whatever coming here, I'll multiply by 100,000, I get the output voltage V out. So what is the output voltage in this case? The output voltage in this case will be equal 10 to the power of 5. Well, this is equal to 10 power of 5 times VR. And I know VR is equal to Vn divided by, multiplied by R, R squared plus XC squared. So what I did, this is VR, and then I multiplied by 10 power 5, right? So I got output voltage. So now I can write that the voltage gain in general for the whole system is equal to the output voltage divided by the input voltage. So if you go to the equation here and just that's output voltage, this is you divided by input voltage, what you got only the things. R over R squared, X squared, XC squared times 10 power 5. So that will be equal to 10 to the power of 5. Let me call 10 power 5 A max, A max. Times R divided by R squared plus XC squared. And our in general, like maximum gain times R divided by R squared plus XC squared. I will do like last time. I'd like to always do that. I'll divide the top by R and the bottom by R. So I got rid of the R in the top. If you like me to do it in steps, I'll just multiply by 1 over R, and the bottom I divide by 1 over R, but just I put it in the square root because I want to get it inside as last time. So I have AM, and then when I go 1 over R squared times R squared will be like 1, and then XC divided by R all square root. Okay, so I got the formula for AV. I'd like to include the frequency in this formula. So we know that XC is equal 1 over omega, which is equal to pi FC. And if I divide by R, so I have R here, so that's XC over R. Great. So I'd like to know the frequency response before I do the both plot, what's happening here. That's the frequency and that's the voltage gain. Now I will see when F is equal 0, what is the value of XC over R? So you put F 0 in this expression. This is expression XC over R. You put F0 in the bottom, so 1 over 0 is equal infinity, so they equal infinity. And the voltage gain, as you look for this expression that you just have, if you put XC over R equal to infinity, so you have AM over infinity, which is equal 0. So actually starting from 0. Interesting. What about if the frequency increased, like reach infinity, almost infinity, huge value? So what's XC over R? I go to the expression here, I see F is equal infinity, so 1 over infinity is equal 0. So XC over R is equal 0. So now I can say that this is equal 0, and I go back to the voltage gain is equal the maximum gain divided by 1 plus 0, which is equal to 1, so it will be a max. So at far it will reach the maximum gain when the frequency gets high. So obviously it starts from 0 and start to increase till it reach the maximum and then continue at the maximum value. Well, what happened if now I try to find where is the cutoff frequency. As we know that the cutoff frequency is equal to 1 divided by 2 pi RC. Okay, so XC over R in this case, it can be expressed, look at, I want you just to pay attention to this, 1 over 2 pi RC, that equal 1 over F, that's F on the bottom, right? Let me just write F on the bottom first. And 2 pi RC left, let me, I will separate 1 times F times 1 over 2 pi RC, okay? This quantity, 1 over F, and the second quantity, 1 over 2 pi RC, that's equal to what? FC. So actually you can say that XC over R is equal FC over F, okay? So now the expression, I go back to this expression and I simplify it more. Now I have A V equal to AM divided by 1 plus FC over F square root. What happened at the frequency when the frequency F equal FC? So at F equal FC in this equation, obviously that the voltage gain will be equal AM divided by square root of 2. Why by square root of 2? Because FC and F, they are equal, be 1. 1 square is equal 1 plus 1 is equal 2 square root of 2, which expected. So if you sketch here line at the cutoff frequency FC, so you'll find the amplitude here equal to the maximum value divided by square root of 2. But obviously this one is different than the other RC circuit that we did when you got out. Here you'll find that at the low frequency the amplitude is really small, the gain is small, then increasing. What does it mean? It means that this circuit you can use it a high frequency filter because it would allow the signal with high frequency to pass without attenuation, different than the other circuit. Okay, in any case, it's not our problem now, but just just to observe that. So this is the how you sketch the frequency response for lead circuit. How can you do the gain? I can tell you exactly similar to the other situation. If you want to do the exact baud plot in decibel, that will be the AV in decibel. I expected that will be 20 log AM and the maximum value, and then it will be decreasing. And I expect that at cutoff frequency, at the cutoff frequency here, FC, it will drop by 3 decibel as we expected. That's general rule. If I want to do the ideal will be turn, let me make it just next to it. If you want to make the baud plot, the ideal one, it will be only straight line, no curves. So I'll say this is F. So it will be a straight line by the same value, which is equal to 20 log A max, and then will be straight line with slope equal, not negative 20, it will be positive 20 decibel per decade.